Good day to everyone. Thank you for attending. I would like to share with you a few slides for the next half hour on application of UHF relay technology to partial discharge monitoring. An overview of what we will discuss today. Really, beginning is looking at really failure rates, why we should think about monitoring of transformers, what the typical defects that can happen in transformers, the effects, also the costs involved in should a failure happen in a transformer. That leads us on to the fact that a large number of the defects are first seen by partial discharge, and this can allow us to detect before failure can happen by detecting the partial discharge. And this leads us on to the why we should adopt UHF technology, and this has been our core business since the beginning of DMS, the application of UHF for partial discharge detection and monitoring. This will lead us on to just a very brief outline of a partial discharge monitor, and also to finish off an important side of the sensing of the partial discharge. There will be the offer of a second session. This is one of two sessions. At a later date, there will be a second session which will take this introduction onto topics relating to this, like location, sensitivity, etc. How important are transformers? Two examples of the effects of a transformer failure on the network. We have in May 2005 a Moscow power blackout due to a cascading fault on the power grid, and it was started by a transformer failure. The effects clearly were huge. Basically 2 million people affected in central Russia, with the stopping of trolley buses, effects in hospitals, water supply. So one component failure in the network has led to a great deal of disruption on the network. And similarly for Chile in 2010, we had a blackout which was due to a major transformer on the southern Chile network, which was connected to the central interconnect network. And here, a massive 15 million people were disrupted by this failure. It took about 2 days to rectify and get all people back on power. So the disruption of one component like this can have a major effect on an overall network. The transformer failure rates have increased over the years. This is a publication by Hartford Steam Boiler Inspection and Insurance Company, talking about the utility transfer assets, transformer assets, and it shows the number of explosions in the US is increasing. The indication there is up to 2002, and also for the end of their design lives, the failure rates will also increase as the aging population of transformers grows. Conditions leading to failures, there are many. this is a breakdown pie chart of this. You have your lightning and through faults. You also have your insulation deterioration, causing major part of the faults, 13%. Inadequate maintenance, moisture, loose connections, workmanship, poor workmanship, overloading. These and others, these are all lead to possible failure of the transformers. A number of these can be preempted by indications that all is not well in the transformer, like insulation deterioration, loose connections, moisture. These can lead to effects like partial discharge, and these, if we detect that, then we can detect there is a fault condition growing inside the transformer. Approximately 60% of failures can be prevented from proper condition asset management and monitoring. This is just an example from the Hartford Steam Boiler Inspection Insurance Company. There are other publications by Seagrey showing similar pie charts and breakdown of fault conditions and percentages. The severity, if you look at the number of failures by cause against the cost of failure, the insulation failure is a major cost and frequency. So if we had the ability to detect that ahead of complete failure of the transformer, then this would be a major saving for the utility. Note here also that the average age of a transformer failed due to insulation is 18 years. It's not like the 40 or 50 years that a transformer is expected to last. The actual failure average is quite low relative to that. Also, with the more modern and faster turnaround of manufacture of transformers, there is and a reduction in the redundancy in the design of the transformers. There is a feeling that transformers in the long term will not be as reliable as the older designs. So we might find that this average age will in fact come down in years to come. Cost of resulting from explosions and fires of the transformers. Clearly the production or the distribution loss is significant. Replacement of a destroyed or damaged transformer is very significant. Just the logistics of removing a transformer from site is still, and getting a new one in at times can be really very, very difficult. The way the surrounding buildings, the area, etc., grows with a transformer which has been there for a number of years. Getting these parts in and out of a station can be quite difficult in today's world. Clearly, the cleanup and repair will be very, very large. Commissioning of a new station or a new transformer in that station, environmental damage caused, any litigation resulting from it, and just your general cost for management and taking care of such a failure. And obviously, health and safety is the most significant aspect of this, and the possible resulting loss of human life, maybe, if we have a really serious situation. As I said earlier, one of the major failures in transformers is due to failure of the insulation, and what preempts that is mainly partial discharge occurs, which allows us to try and identify when the insulation is in a fault condition. Applying a PD monitoring system allows you to have a very early warning system that changes are happening inside the transformer, and that long-term trend monitoring, or if need be, almost immediate action can be taken to stop any catastrophic failure of the transformer. You can also relate it to things like switching events, where it's been on high load relative to the PD activity, etc. So you can actually see how things are instantaneously changing with these events. It is a good indicator that the insulation system is healthy or not, and especially it also gives you the trend over time. DGA has been used for many years, and is really the basis for monitoring at the moment on transformers. It's not that the use of UHF or any other technique would replace DGA. It's rather that the two of them go hand in hand. The use of UHF PD detection is, as I said, an early warning system. It allows good trends to be measured for the PD activity. Also, along with the DGA, you can tie the two together. There is a history of knowing when particular gases get to a particular level that the transformer is in a difficult state, and hence should be taking an outage on the transformer or the load reduced. That is based around very much on gas analysis. So the two go hand in hand, we believe, not one against the other. Type of PD sources which happen in transformers: really bad contacts, where you get microsparks between conducting surfaces separated by thin layers of oil. For example, loose nuts or bolts, maybe in tap changers. Large components like floating electrodes, where we have some stress shield or some large piece of metal which is not securely bonded to earth or to the high voltage parts in the bushing connection. Suspended particles in oil, these can also discharge if they go close to high voltage conductors. And rolling particles, maybe they're too heavy to actually be within oil, but are in the bottom of the tank or on the surface of the core or winding, and these can also cause discharge. And protrusion, sharp points, metal protrusions on conductors or exposed maybe breaks in insulation. Also, surface discharges on the press board surfaces due to moisture or damage. This leads to surface tracking, loose cable connections, terminations, and voids, air bubbles in the oil, or in any epoxy or press board. These will also discharge. So we're looking for basically a technique which will be able to detect all of these types of defects. Before going on to discuss that, the last slide really on this part is to do with the cost-benefit analysis. Seagrade did publish a brochure in 2004 on a guide to the economics of transformer management, and it related basically a rated power transformer, 100 MVA, the costs for repair or replacement, and then also cost for early detection of a problem in the transformer, and it then defined various probabilities to do with failure and monitoring and outages, etc., and the cost of replacement. And if you work out an annual cost with and without monitoring, you can show that there is an annual saving of, in this case, it was $21,737. Clearly, if you multiply that up by the number of transformers that a utility may have, also varying the parameters, the costs might be higher, etc. So there is a saving can be shown, and also in terms of actual monetary saving, but also benefits in the fact is that the transformers are being monitored 24/7, and you have the ability to take action before a failure happens. How would we detect PD in transformers? There's a number of techniques. There's basically non-electrical discharge detection and electrical discharge detection. Non-electrical, chemical, DGA, is a standard at the moment. Acoustics, also light, heat. These can all be measured by various ways on the transformer. Electrical, you can use the IC270 method. Also, you can use RF emissions, and this would be either HF, high frequency, very high frequency VHF, or UHF sensors. And it is the UHF sensors that we use to detect PD in transformers. The UHF type of sensors allow real-time and accurate defect location, real-time detection and accurate defect location to be made in the transformer. Why adopt the UHF technology? Well, it's a well-proven technique. It's very sensitive. It's applicable both for continuous and periodic measurements. You don't need a lot of sensors on the transformer to detect the PD. You need a few more in order to do location, but you don't need many sensors on the transformer. It's also been used in gas-insulated substations for many years now, almost over 20 years. So it is a proven technology for partial discharge detection. The sensors themselves are robust, passive, fixed sensors, and are expected to last the lifetime of the transformer and not require any calibration in that time. The UHF technique for detecting the signal created by the PD is less sensitive to noise because we're in a different band from the normal air corona or radio frequencies that we know we can filter out. So there's less signal processing compared with using CTs or TEVs or HF or ultrasonics for the PD detection. It can be applied in the factory as part of routine tests, also in the field, or for continuous or periodic monitoring of the assets. We can detect time-lagged external events that may be integrated within a wider monitoring strategy. What we mean by that is that it's the relationship of the PD activity to, say, the change of a tap changer or the load on a transformer. External events can have an effect on the transformer and its PD activity, and we can correlate these. The UHF and DJ, as I said, are complementary. Seagray has proposed in 2008 that in future transformers should be fitted with DN50 valves or windows on which UHF couplers sensors can be mounted and used for monitoring either periodic or continuous. There is a working group A2.27 who published brochure 343 discussing this and recommending this at that time. The oil valve probe, because the recommendation is very much focused on use of valves or windows, then the valve probe coupler will become increasingly important for new fits, but also particularly for retrofitting for existing transformers. What is the principle of the UHF technology? How do we detect PD? Well, when a PD happens, it's a microspark. It's a very fast current pulse, and when the discharge happens, it emits sound, it emits light, but also emits electromagnetic wave, similar to the interference in your car on the radio and due to the spark plugs. It emits electromagnetic wave which propagates through round the tank and reflects from the tank walls. Also, if you place a sensor, a UHF sensor, within the tank, then you can detect the UHF pulse. The UHF band is from about 200 megahertz up to over 2 gig, and the range for a tank, a typical transformer tank, would be between about 300 and 1 gigahertz. So hence the use of why it's called the UHF technique, because we're working in the UHF band. The signal we have is a very wideband signal, and we can pick up parts of that frequency range and still detect the PD signal. It transmits in all directions from the source, so we place couplers at various positions on the tank, which we'll talk about later, and there the signal will be picked up and indicate that some PD activity is happening. The actual sensors themselves we'll talk about in a few slides from now. I won't get into detail here. The PD location, we can, using the time of flight technique, accurately locate a PD if we have something like 4 or 6 sensors, 4 in a smaller transformer, 6 in a large transformer, then we can basically locate a defect down to a beach ball sort of sphere of location. So we can get accurate location to a very small part of the tank where that PD is. Identification also, the pattern by phase resolving the PD activity to the power frequency of the transformer, then we can characterize the fault, say what type of defect it is. At the moment we're building up our database on this. You need a lot of data to be able to create automatic identification expert systems. We are in the middle of doing that. We're building up our database rapidly now with the number of installations we have on transformers. So we will eventually have an expert system based around transformers. To detect the level of defect PD in terms of picocoulomb level, we have been working for some time to determine a picocoulomb level. The UHF technique itself directly does not give a picocoulomb level, but we can, using various techniques, come out, basically estimate the picocoulomb level, and actually the session 2 will discuss that. Suitable for real-time monitoring, we have a number of transformers in the world continuously monitored at present on a 24/7, and we can look at the data and see whether it's changing with time or load, etc. And as I say, it allows us to basically monitor the fault evolution and also the inception when a new PD has started within a transformer. What levels are significant in transformers? Again, Seagray published a brochure in 2003. It's basically set out these 6 levels, starting from defect 3, which was 10 to 50 picocoulombs, normal deterioration of 500, and questionable, where an investigation would be implemented, would be anything above 500 picocoulombs, and really they're saying anything above 1,000 is really a defect condition, and over 2,500 is saying it cannot be reversed, and clearly anything above that, 100,000, you are in a critical situation in terms of a major discharge within the transformer. These levels are under review by Seagray, and talking to people, they are saying that they expect these, like the 500 level, to come down, or possibly to 300 or even less. What constitutes a monitoring system? Like all systems monitoring, you require a sensor. In this case, we have either internal sensors, window sensors, or valve sensors, and we'll discuss them in more detail in a little while. monitor itself is really just a data acquisition system, which samples the data coming from the sensors, formats it by phase resolving it to the power cycle, and then analyzing it, plotting it, trending it, reporting on it is the final analysis section. And eventually we will have expert services or expert system to automatically analyze, or at the moment we're doing very much expert services reporting on what we see. Now, line of a monitoring system, we have our couplers placed on the transformer. They're cabled by UHF cable, high frequency cable, down to data acquisition. In this case, it's what's known as a 609 PDM. And here the data is formatted, phase resolved, stored, displayed, communicated out to some external remote client application. If we want to add on more transformers, then we can add on an OCU unit, basically another box which takes the signal from the couplers, conditions the signal and analyzes it, formats it, and sends the data down to the 609. So we can do multiple OCUs, allowing us up to 24 sensors in total for one 609 system. We apply external noise sensors through an antenna. This is in case the noise is very severe. External noise is very severe on the site. But in general, because the tank is very enclosed, then the noise level in general is very low within a transformer for UHF signals. The examples of the types of couplers we apply. The window coupler on the left, here in the bottom left, you're seeing a tank wall, transformer wall. We have an outer sleeve which is basically in contact with the oil, and we have an inner sleeve with a coupler inside, and that's mounted on a flange. So the coupler itself is not in contact with the oil, but the outer sleeve allows the safety of the coupler not being in touch with oil. Some utilities don't like the sensor being in contact with oil in case it falls off and it falls into the oil. In fact, the sensor itself is very much a mechanical, very robust mechanical design. So we actually also supply internal couplers directly into the oil, and also window couplers where the same type of coupler is held is mounted within a window to prevent it falling into the transformer. These sensors can be put on the tank wall, as seen by the top middle picture, or also on hatch covers in retrofit situations where we put, say, couplers in the top hatch covers of the tank. The top left is actually a similar sort of design, where we were asked to do investigations in a tap changer of a transformer, and this was the filling plug, oil filling hole for the tap changer, and we designed a coupler to fit onto that. On the right hand side we have a drain valve. Here we can insert a sensor like the one shown in the middle picture, with the sensor, the black point at the end is the sensing part, and a flange to connect to the standard oil drain valves, and with a handle and UHF connection coming out at the other end. The types of valve that we can insert such a drain valve in a drain probe is ball valves and gate valves. These are okay because they give us a direct line of sight through the valve itself when opened. The globe valve or stop valve, because of its design, we cannot go around basically the bends. We don't have a direct straight through path, so these are not suitable for us to put these probes in. Here's an example of the valve probe connected onto a tank in the top right hand corner. This is just showing you the configuration, maximum stroke that we can insert into the tank. We don't insert the probe all the way. This insertion would only be the head of the sensing part, which is about 60-70 millimeters in length. So we're not inserting all the way into the tank. It's only a short distance. Here we have some window couplers mounted on the tank wall. In the bottom picture we can see a sensor fitting. This is a window sensor. It's on a 400 kV phase shift transformer. We had six sensors on this transformer. Here we have another situation where we have in the bottom right we have actually a 800 MVA series reactor which went into Hong Kong, and here again we had 6 sensors because of the size of a tank. And just up above that you see one of the couplers mounted onto the tank wall. This was clearly these were installed during manufacture of the tank. And in the top left here we have a situation where we're trying to retrofit to an existing transformer, and they were putting couplers at the top and at the bottom while it was being refurbished. Where would we put couplers on these transformers? Well, really, the sensors, it depends whether you're wanting purely detection or if you want location of the defect. And most utilities want to know where the defect is. It's the first question. And in order to do location of a defect, then for a typical single phase transformer, I'll say maybe 4 meter tank by 2 meters by 3 meters high, then we need four sensors to give us a beach ball location or a football size location. The top right hand drawing shows the positions of these couplers. Basically they're in a diagonal formation on opposite walls of a transformer, with the diagonal swapped over from one wall to the other wall. So they're basically not all in the same plane. You're basically trying to create a very spatial spacing and positioning of the couplers. For a typical large 3-phase transformer, you really want 6 sensors for location, and typical maybe up to something up 8 meters by 3 meters by 4 meters high or larger, then you'd want it as a triangular distribution on a wall. So you have one triangle on in the bottom right hand corner on the front face of the tank, and the back face you'd have a similar triangle, only inverted. So you basically again get this distribution of couplers. Clearly this is these are our basically standard positions. We don't need them exactly this, but we're looking for them in these general areas. But clearly they would change depending on the shape of the tank, where the tap changer is, because we'd also monitor the tap changer at the same time. We don't want the sensors to intrude into the high field area, so we particularly use window sensors around the bushing area. Clearly, the sensors placed near the bushings allow a closer monitoring of the actual bushings themselves for any real activity in the bushing or in the connection to the bushing, which is really important. And the lower sensors, these could be drain valves, existing drain valves if it's a retrofit, or it could be even in a new build. So in new transformers, generally sensors are fitted by the OEM. Generally at really low cost very low cost relative to the actual transformer cost itself, and there's no real effort in terms of the OEM. Very straightforward to do, and we've done this many times with a number of OEM suppliers. In service transformers becomes a bit more difficult. Clearly we try not to have any oil work, so we'd first look to see how many where the drain valves are, any other valves that we could use, using any hatch covers at the top of the tank, so that there's very little oil work required. So we're looking to very much use parts which don't require or require very little oil work. As I said, the sensors are very simple, very robust, and contain no active parts, and are expected to last the lifetime of the actual transformer.